So with this one, with our logarithms, something I'm keeping in mind here is that if I'm taking the logarithm of 1, that comes out to 0. So right now what I would have if I plug in x equals 1 is I would have a bunch of zeros, but most importantly in the denominator I would have a 0. So with that I'm going to need to make some adjustments here. And the properties we're going to run a review here come from our logarithm properties. So, up in the numerator, what I'm seeing is I'm adding two logarithms separately. So what I'm going to do is combine those. So I'm taking the limit as x approaches 1 still. And what we can do is when we're adding two logarithms, I can combine them into a single logarithm where inside the parentheses, I'm multiplying the previous insides that were separate. So here I would have x times the square root of x. So that's one of our logarithm properties. We're going to use this similar one with subtraction in the denominator, but before we do that, we need to be aware of these numbers that are outside. And what we can do is a logarithm property says that those can come inside the parentheses as an exponent. So what I'm going to do is keep them separate. What I'm going to do is have it as the logarithm of x to the 6th power minus the logarithm of, and we already have x cubed. So what that's going to be is we'll have x cubed, and when we have power to a power, we multiply. So that's really going to be the logarithm of x to the 9th. Okay, so that numerator is going to be pretty much done. I'm going to make an adjustment, but just for the sake of kind of using up our logarithm properties, the last logarithm property, well, maybe not the last, but the next one I want to use is in the denominator when we have subtraction. What we can do is change that to division of the inside values. So we're taking limit as x approaches 1. We're going to have natural log of x root x over, and down here I'm going to have the natural log of, and this will be x to the 6th over x to the 9th. All right. As I'm doing this, you could keep trying to plug in +1 like each time you evaluate it, but we're still getting a denominator of 0. So that's why we have to keep going here. Okay, in the numerator, what I want to do is simplify that expression x times root x. So this is the same as x times x to the 1/2. So I have x to the power of 1 times x to the 1/2, and our exponent property says we can combine those by adding those exponents together. So that's really the same thing as x to the 3/2. So what I have up there is the natural logarithm of x to the 3/2. In the denominator, if we carry out that division, I'm going to go ahead and write it as a negative exponent. So we'd have x to the -3. Coming from, we're just going to review all of those exponent properties too, where you take x and then you subtract the exponents, and that's where we get that x to the -3. Okay, we're using lots of side properties here, but it's good to get a review of these. Okay, so what we're going to do is go back to that rule that we used at the beginning, where we brought those numbers inside as exponents, and we're going to do the reverse, which lets us take those values and put them out front. So that would let me go equals, we still haven't evaluated the limit, I'm just simplifying the function this whole time, but we have 3/2 times the natural log of x over -3 times natural log of x. If I still plug in x equals 1 here, I'm still getting a 0, but now we get a nice cancellation of these natural log of x's. We can cancel those. So really, I actually just end up with a constant. So I'm just ending up, and let's go ahead and write it as limit as x approaches 1 of, oh, let's even get review of this. We have a complex fraction there. Oh yeah, let's go 3/2 divided by a -3. This is some really good review. And if we have a constant, the limit, it doesn't matter because we don't have anywhere to plug in x equals 1. So what I can do is just evaluate 3/2 divided by a -3, which is the same as 3/2 times a -1/3, which will be a -1/2. So that was my keep, change, flip. We keep, change to multiplication, flip to the reciprocal, and then simplify. That one had a lot of good logarithm properties, exponent properties, even just some general arithmetic properties with complex fractions, but all to get to a point where we can evaluate that limit. And again, if you want to check your answer with that, go ahead and graph the function and look at what's happening as x approaches 1, and it should be approaching a -1/2. Okay, so with that, let's go to lots of scenarios here. If that was a good refresher of some algebra for you, these might be good to pause this video, try for yourself, and then use it to check your answers. But I find with these limits, the more examples, the more helpful that is, because of all the algebra properties we need to bring into it. Okay, this first case looks like I can just plug in 0. So I'm going to have -0 cubed plus 2 times 0 squared minus 3, which should all simplify to a -3. And with all of these, I could check that answer by graphing the function and evaluating graphically like we did last week. Okay, with this one, I would try to plug in -3. And actually, let's just see if I do -3 squared plus 8 times -3 plus 16. So we're going to have 9 minus 24 plus a 16, which should be a -15 plus 16. So we're going to be all good just plugging in -3 here. So I'm going to have -3 plus 5 in the numerator over this -3 squared plus 8 times -3 plus 16. So that's going to be a +2 over 9 minus 24 plus 16, which is going to be a 2 over 1. So that's all going to just simplify to 2. No special properties we need to plug in, is just plugging in that value for x. This is where we're taking the limit of a constant function, which means it just stays that constant. There's nowhere to plug in x equals -1, so you just use the constant. Here our function's just a simple x, so we just take x equals 3, plug it in. With this one, plugging in 1 is going to be an issue, so what I want to do is rewrite this limit as its factored form so I can take care of that hole in the graph. So multiplying to +4, but adding up to a -5, so we're going to need an x minus 1 and an x minus 4, all over x minus 1. So we get our cancellation. So I'm really just evaluating the limit as x approaches 1 of x minus 4. So 1 minus 4, which is a -3. Plugging in 3 here also causes an issue with a denominator of 0. So what I'm going to do is continue to evaluate that limit, but let's go ahead and factor. We have a common factor of x in the numerator. And if we factor out x, we'll get x times x minus 3, and those x minus 3's cancel. So really, I'm evaluating the limit as x approaches 3 of x, and plugging in x equals 3, we'll get a 3 out. Okay, here's a little extra review. We didn't see one of these scenarios, but this will be good practice of what to do when you have a complex fraction like this. And what we want to do is multiply the numerator and denominator by the least common denominator, which sounds weird because we have like denominators of denominators. What I'm looking at is, in this case, just that -1 plus x. I want to multiply everything in the numerator by that -1 plus x. I want to multiply everything in the denominator by that -1 plus x. So what that's going to do is I'm evaluating the limit as x approaches 1, and in the numerator we're going to have x times -1 plus x. In the denominator, I have that 1 over -1 plus x. That's going to be multiplied by a -1 plus x. And then I also have that plus 1 that's also going to get multiplied by -1 plus x. So what I did is I just made sure that everything in the numerator was multiplied, everything in the denominator was multiplied. So down here, it's like it distributed into the parentheses. So what that will do is we'll get a nice cancellation right there up in the numerator. And I'm debating, I'm going to go ahead and keep it factored just in case something else cancels out. So I'm going to keep that as x times -1 plus x, just in case something else comes up in the denominator as I'm simplifying. But we're going to have a 1 and then a -1 plus x. And with that, we'll have the limit as x approaches 1 of x times a -1 plus x over x. I could go ahead and plug in 1 at this stage, but we could even see like those x's cancel. So if you keep simplifying until it's fully simplified, or you could go ahead and plug in just as soon as you can, but we'll be plugging in and we should end up with what, -1 plus 1, all of that to get a 0 out in the end. All right, this next case, we're going to be doing the same thing, except this is a scenario where I have 2 denominators. So I have a 3 plus x and a 3. So multiplying by the least common denominator, what I'm going to have is times 3 times a 3 plus x. And then same thing down there. So up in the numerator, see, we're still taking our limit. Up in the numerator, we're going to have a 3x times 3 plus x. Down in the denominator, what's going to happen is that 3 times 3 plus x distributes in. Let's go ahead and write that at this stage, where basically this gets multiplied by 3 times 3 plus x. This gets multiplied by 3 times 3 plus x. So we'll get these nice cancellations. So first we'll just have a 1 times 3, which is 3. And then over here we'll have a -1 times 3 plus x. So we'll have a -3 minus x. And we'll go ahead and keep simplifying. So that'll be 3x times 3 plus x. Again, just keeping that factored in case things simplify more. So that'll be a -x down there. We'll get nice cancellations of x's, but we still have this negative hanging out. So this will be the limit as x approaches -3 of a -3 times 3 plus x. So if you're wondering where that negative came from for 3, it came from down here because that was a -x. But it's just like dividing by -1 is the same thing as multiplying by -1. Okay, let's go ahead and plug in -3. So we have -3 with a 3 plus -3. And that's going to be a 0. All right, a few more examples here. It's a case where, okay, if we plug in 9, we run into an issue. There isn't anything to factor, but what I'm seeing is in that numerator, I have that binomial that involves a square root. So I'm thinking I want to multiply by the conjugate. So having a root x plus 3. So I'm getting that difference of squares. And whatever we do to the numerator, we have to do to the denominator as well. So in the numerator, we're going to get our difference of squares. So I'm going to have root x squared minus 3 squared. In the denominator, I have this x minus 9 times root x plus 3, and I'm going to leave it factored like that. It doesn't really benefit me to multiply that out at this point. So I'm going to leave it factored after I see what happens to the numerator here. So the limit as x approaches 9, root x squared is just going to be x, minus 3 squared, which is 9, over the x minus 9 times root x plus 3. And glad I left that factored because those x minus 9s cancel. So this is the same as evaluating the limit as x approaches 9 of 1 over root x plus 3. Now I can go ahead and plug in 9. So root 9 plus 3, so a 3 plus 3 for a 1/6. Okay, similar scenario here. It's just in the denominator, but the process is the same. So I would try to factor, but there's nothing to factor. So instead, with that square root of x minus 2, I want to multiply by a square root of x plus 2 to simplify things out. So we're still taking the limit as x approaches 4. And in the numerator, I'm going to keep that factored after I see how that denominator simplifies. So I'm going to have root x squared, which is x, minus 2 squared, which is 4. We get a nice cancellation just like we want. So really we're evaluating the limit as x approaches 4 of root x plus 2. Now I can go ahead and plug in 4. So 2 plus 2, which is 4. So again, I just want to emphasize with this limit notation, I'm keeping the limit notation until I plug in that value for x. So it's very important because we're still evaluating the limit this entire time. It's just that we can apply those limit laws when we make these substitutions for what x is equal to. Okay, last example here. I know this is a long one, but with a piecewise function, we kind of looked at how to do this with a graph. What we'll do is look at how to evaluate this algebraically. So we're approaching 2 from the right-hand side. So with that, what we're going to have is we have two functions, negative 2x plus 8 when x is less than 2, and x minus 1 when x is more than or equal to 2. And something I like to do in terms of a visual here is you could think of a number line. So 2 is where we're switching functions, and here's 1 and here's 3. So let's see, when x is less than 2, so not equal to, but less than, we're using negative 2x plus 8. When x is more than or equal to 2, so when we equal 2 and everything above, we're using x minus 1. Then what I want to evaluate is we're approaching 2 from the right-hand side. So what we're doing is we're coming at 2 from this side, which means as we're approaching, we're looking at x minus 1 as our function. So what I can do is evaluate this limit with the function x minus 1. And what I would do is go ahead and plug in 2 minus 1, which is just equal to 1, and that would be our limit. Now, if this was the limit as x approaches 2 from the left-hand side for our function, what I would do is if we were approaching from the left-hand side, I would be using the negative 2x plus 8. Because again, it's what's happening just to the left of 2. So with that, I would go negative 2 times 2 plus 8, which is 4. So just to show the difference between left and right with these piecewise functions. And then the only way we could do the two-sided limit here is if these were equal to each other, if one was equal to 4. But they're not, so if we tried to do the two-sided limit, it does not exist. But individually, right and left, we can evaluate that, and I just find this number line really helps me to see which function am I using on which side, so then I can be real careful of, okay, from the right, we're using this. From the left, we're using this.